Good morning. We are going to today talk about rotational dynamics. So more rotational stuff, and once again, the rotational stuff will not be on the test, but we will be going over topics that are energy and that will be on the test. So that is the energy topic. So it helps to review still for the test. On Monday, it will be just reviewing for the exam. So let's get going. Start with torque and angular momentum. Angular momentum is the propensity to, well, maybe I should back up a step. We learned Newton's second law, Newton's first law. Newton's first law is called the law of inertia sometimes because it defines that things have a natural tendency to keep going at a constant velocity unless something acts on them. And that tendency to keep going at a constant velocity is dependent on the mass. The more mass something has, the more it's going to resist changing its motion. And so we call that property of resisting change in the motion inertia, and the more mass an object has, the more inertia it has. So Newton's first law gave us the law of inertia, saying that things will stay in constant motion unless a force acts on it. Then Newton's second law said that the relationship between the acceleration produced by a force and the force itself is the mass. That is, the acceleration is the net force divided by mass. And do remember for the test that acceleration is net force over mass, not acceleration is force over mass, or not F equals ma. Right? F equals ma is patently wrong. The ground is applying force to me, and I am not accelerating because of that. Likewise, gravity is applying force to me, and I'm not accelerating from that. But net force equals ma is correct. You add up all the forces on me, they add up to zero, and hence I'm not accelerating. Now, going to rotation, if you think about it, when something is rotating, each particle is moving and has inertia. And so if we were gluttons for punishment, we could go ahead and calculate what's going on for each particle in a rotating rigid object and never worry about the rotational calculations. But that is very hard. So instead, we take a rigid object and we say, okay, they're all rotating at the same rotational rate. That is, they're all completing the same number of rotations per second. And so let's make calculations on that rigid object that includes all of the little particles in it. So with that in mind, we have the idea of angular momentum and the rotational equivalent for inertia, which we'll call either the moment of inertia or the rotational inertia. And so that is the resistance to change in rotation, which is just the resistance to change in motion applied to rotation. So I have here a couple of pictures of rotational things, and I want to do a simple illustration with just any random person who's willing to sit in a chair and spin. James already has his hand up. All right, come on up. Now, I am without my heavy masses. Especially with a big fellow like James, I need my heavy masses, so we have some appreciable mass to deal with. So let me grab some big protein to sit and spin with. Assuming I find it. You're not. If I do this quicker, I'm going to toss them. That would be a very bad idea. It's not a unicycle. Okay. So here is James, my intrepid, man, your arms are so long, this might be a problem. My intrepid demonstrator. And so I rotate him. Now you got to take your feet off so you don't stop. And he spins. Now if he puts his hands out, he slows way down. Brings them in, speeds up again. Now, of course, it's a lot more fun to have him hold his hands out first. Hold your hands out. Then I spin him. And then he pulls them in. And now he's like a figure skater, right? Figure skaters start their spin with their arms and legs out. They pull them in and they speed up. Why?
They're decreasing the radius.
Okay, they're decreasing the radius. What difference would that make, though?
And that has an indirect correlation with the amount of torque.
It has to do with torque, but it actually is working because the net torque about his vertical axis is 0. There is some friction in the bearings, but we're assuming it's 0. So there's no torque in the vertical direction. And if there's no torque, I know you want to say, if there's no torque in the vertical direction, then Newton's second law, for the linear, it was net force is mass times acceleration. For rotation, it's net torque is the rotational equivalent for mass, which is the moment of inertia, times the rotational velocity, the angular velocity. And so the net torque was 0, so that means that he should have had the moment of inertia times the angular velocity staying constant. Well, clearly he brings the mass in, his angular velocity increased. So that means that his moment of inertia had to decrease when he brought them in. So we can see there's a relationship between, actually, go ahead and sit down. I know. It's kind of fun to sit up here. I'll call you back up later for the second half of the demo. So we can see that the moment of inertia has something to do with where the mass is located, which was not the case for your normal inertia. Right? It doesn't matter if all of your mass is in your head or in your belly, you have the same inertia. I set this down so I have to come back. I usually demonstrate the figure skater. You know, they start like this, they spin, and then they pull it in, they spin faster, right? I too could fall down. I actually couldn't spin. What did you want to say, Leslie?
No. I was just gonna say, talking about how like the closer you are to like the middle, the center, what is it called? The
rotational axis.
Yeah, there you go. The rotational axis.
Okay, so we have to introduce a new variable, L. L stands for angular momentum. I don't know why. There's no L in there's an L in angular, but it's not an important L, right? It's there at the end, and there's not a momentum. But L is the symbol we use for angular momentum. Notice this is a bold L. It's a vector. I'll draw vector signs on top just to make it very clear. Angular momentum is a vector. But the weird thing about angular momentum is this direction. Rotation. Okay, when we talked about velocity, if I'm running like this, my velocity is the direction I'm traveling. That makes perfect sense because it has to have a direction. The direction I'm traveling seems the obvious direction to make it. But if something's rotating, everything is moving in a different direction. But they're all moving in the same plane. In this case, I'm rotating and everything is moving in the horizontal plane. So the direction that we assign for rotation is the direction that is normal to that plane in which everything is rotating. So since everything's rotating in the horizontal direction, what direction is normal to horizontal? Vertical. And so, did you have a question, Emily?
No.
Okay. So angular momentum or angular velocity is going to be in the direction that's normal to the velocities of each individual, for each individual one it's perpendicular. But if it's perpendicular to each one, it has to be normal to the plane. And we get the direction we assign for the angular velocity with the right hand rule. You just wrap your fingers in your right hand. You wrap the fingers in your right hand in the direction of rotation, and your thumb points the direction of the angular velocity. So once again, we look at the clock. We talked about this before in terms of torque, but now it's real simple in terms of angular velocity. The second hand is moving as you look at it clockwise, because that's how we call clockwise, how we name it. So if I wrap my fingers in the clockwise direction, they're pointing into the clock. And so the direction that the second hand is traveling, according to physicists, is its angular velocity is into the clock. I can't say the direction it's traveling. I have to be more precise. Direction is angular velocity is into the clock. And traditionally, that would be called negative. Since the angular momentum is moment of inertia I times angular velocity, then the direction of the angular momentum is the same direction as the angular velocity. Just like linear momentum was mass times velocity, the direction of linear momentum is the same direction as velocity. So what is this I? We didn't go through any calculations for it, but it turns out that the definition of I is the sum of each individual piece of mass times the radius of that individual piece of mass from the axis of rotation. So it actually depends on the axis of rotation. If I take this cylinder and I spin it about the center, then I'm going to have to add up the radii from each little piece of mass squared times that piece of mass. How would we do this? Or people should answer with an integral. Everyone else would say, but I'm not in calculus-based physics. And in that case, you trust somebody who's done the integral and you look at a table. So the moment of inertia for spinning around the center of mass in this disk is 1/2 the mass times the radius squared. If you spin around the edge, you have mass that's significantly farther away than 1 radius from the place it's spinning. And so the moment of inertia is going to have to be larger because the mass is farther away. And so if you look there, we don't have the equation for it spinning around the edge, but it's going to be, I think that it comes out to be 2mr squared if it's going around like this instead of going around the center. I'm going to do a demonstration involving that. This is a hollow sphere. A hollow sphere, thin spherical shell, is 2/3 mass times radius squared for its moment of inertia. A solid sphere, on the other hand, is 2/5 mr squared for its moment of inertia. Those come from calculus calculations. And you can see lots of other variations. You have a rod spinning around its center is 1/12 mass times the length of the rod squared. Spinning about its end of its axis 1/3 mass times the length of the rod squared. You might have had a question in your reading quiz about a rod that's tied to a string. Let's first take the simplified version of that. Not this one, this one. Here I have a stopper tied to a string. If I swing the stopper around a circle, it has a certain moment of inertia, and for all intents and purposes, I can treat that stopper as a point mass. And so I just say, sum of mass times radius squared is the mass of this thing times the radius from the string to the center, from my hand to the center, squared. So I just take that and say that's effectively it. Now in practice, it's slightly bigger than that because this thing is also doing a little rotation. But that's pretty close. So that reading quiz question, where you had a rod that was 0.4 meters, okay, so it's not just a little bob, it's not a point mass. If you wanted to do it right, you would have had the mass of the rod times the distance to the center, or distance to the center of mass squared times the mass plus what you get from rotating around the center. So plus 1/12 ml squared. So just for, I set stuff down all the time. This is like key to my lectures. So for that problem, for the string with the rod at the end, if this is R and this is L, then the moment of inertia, the correct moment of inertia would be mass times R plus L over 2 squared plus 1/12 mL squared. That would be the correct answer. But notice, since R was 3 and L was 0.4, 3 plus 0.4 over 2, or 3 plus 0.2 squared, is much, much bigger than 1/12 of 0.4 squared. And so the answer they gave you was approximately correct. And that's why it said approximately correct and not exactly correct. So how do you get these moments of inertia for homework problems? Unless you're in Physics 251, you look at the table, right? No one's expecting you to memorize that table. You should know the equation, or of course it'll be given to you on the test, but you should be comfortable with this equation for the moment of inertia. So if you have, for instance, one object that's a radius r away, you should be able to say, the moment of inertia for its rotation is mass times radius squared. But you're not expected to say, it's a square. So clearly, for a square object, or for a rectangular object rotating about its center, it's blah, right? No one's expecting you to remember that. Now on this page, I have lots of equations. And each one of these equations is rotational except for the first one. The first one is our definition of kinetic energy, 1/2 mass times speed squared. It's a scalar, has no direction. When we have something rotating, we have each piece has a different speed. And so once again, it's hard to talk about the rotational kinetic energy. I can have a wheel like this. And if it's spinning, each piece of the wheel has a kinetic energy. And if I want the total kinetic energy of the wheel, I either do a hard calculus problem or I ignore the fact that there are spokes in the wheel. And I say, this is a hoop that is rotating about its center. And for a hoop rotating about center, the moment of inertia is mass times radius squared, because all of the masses are distance r away from the center axis of rotation. And then I say, well, kinetic energy for rotation can be written as, and I actually don't have the full-on equation written there, do I? Going through the conversion, this is what V is. V is omega r. And so I have 1/2 mr squared omega squared. I forgot the square there, my bad. Which is 1/2 I omega squared. So that's the equation for the rotational kinetic energy. Notice it's the same as the normal kinetic energy, except for m has been replaced by I, and v has been replaced by omega. And that is the theme for rotational calculations. If I was lame, I could just stop here and would be good. Every equation you've done for dynamics, you can just replace the m with the I and the v with the omega, and theta for x, or replace x with theta, and acceleration with alpha, and you have it. But of course, we want to have some more understanding than just that. So kinetic energy, rotational kinetic energy is 1/2 I omega squared. Angular momentum is I omega, right? Linear momentum was mass times velocity. Angular momentum, you replace mass with I, moment of inertia. You replace velocity with omega, the angular velocity. And so angular momentum is I omega. But there is another form of it. That's why it would be very lame to stop there. The other form is R cross P. What does R stand for? radius. That's the radius from the axis of rotation to where your little piece of mass is. And then what does P stand for? Momentum. And now the hardest part of this equation, it has, I said R cross P, I didn't say R times P. Because they're vector signs, that X doesn't mean times, it means cross. And cross was multiplying the perpendicular components. So it's a cross product to get the angular momentum, R cross P. Torque was R cross F. You can see the similar relationship between torque and angular momentum, which gives us the rotational equivalent of Newton's second law that says the net torque is equal to I alpha, or I times change in angular momentum multiplied by change in time. Now that last equation is really unique and cool. Let's do some fun things with that. So looking at that equation, torque net is equal to I times delta L over delta T. I can solve that equation for, I had it in my hand like a split second ago. There it is. I can solve that for change in angular momentum is equal to torque net times, there's no I there, times delta T. That's a mistake on my part that's pretty brutal. Net torque is equal to change in angular momentum over change in time. I am sorry about that I wrote it down not thinking. So change in angular momentum is net torque multiplied by change in time. So if I have this thing and it's spinning, it has an angular momentum. What direction is that angular momentum pointing right now? Okay, right now. You can see the direction of spin easily. Okay, I have competing answers. So, Clayton, tell us how you get your answer. Okay, so let's start with which hand you use. Your right hand. And then how do you orient your fingers? So they wrap the direction it's rotating, and then your thumb points toward me. So the angular momentum is pointing toward me. Now, if I were to hold this by the end, then gravity would be making a torque. What direction is the force of gravity acting on this wheel? Down. And so if gravity is acting downward, and it's acting in that direction from my pivot point, what direction is the torque? Okay. Ryan did it correctly. He put his index finger in the direction of the radius from the pivot point to where the mass is, middle finger in the direction of the force of gravity, and the torque is forward. Now I've rotated the direction here, so the angular momentum is toward me, and the torque is toward you. So according to that equation, the change in angular momentum should be in the direction of the torque. It should be toward you. But right now, the angular momentum is pointing toward me. So what's the wheel going to do if I just hold it by this pivot point according to that equation? It's going to have to rotate so the angular momentum direction changes according to that equation. So the angular momentum is going to have to move out that direction, which means the wheel is going to rotate that way. So now, of course, we test and see. And you can see, sure enough, it's slowly falling down, not nearly as quickly as it would have fallen down if it wasn't spinning, but it was going around the circle. And I can do crazy things like I can make it go back up by forcing it to spin. Is that cool? This is why we use gyroscopes. You have angular momentum, and then if you make it so there's no external torques, it will try to maintain the same angular momentum. And so if there's no external torques, if we're like a spacecraft and this is just on gimbals and the spacecraft changes its direction, this will just rotate so it stays the same direction. So you know, that's the direction it was going. So you can use this to keep your bearings. Of course, you have to keep it spinning, and you have to make sure you have very little friction, or else, well, you have the problems that we see in all of our real-life examples. It's kind of fun to play with these. Some of my favorite things, I know you guys grew up with shows like Punk'd and whatnot. When I was a kid, there was Candid Camera with Alan Funt. And one of the great ones he did was he took a suitcase, and in that suitcase, they put a wheel like this. Now this wheel has a bunch of copper wire around the edge. Why? Because that gives it a big radius for the wire, as big as possible, which makes your moment of inertia as big as possible. And then you have this in a suitcase, and the suitcase has a little motor that spins it really fast. And so if it spins really fast, if you take it and you walk forward, there's going to be no problem. But what happens as soon as you try to change directions? Like if it's spinning like this, so it has its moment of inertia toward me. If I try to turn it like this, what's going to happen?
It's going to release.
It's not just going to resist. If I try to turn this like this, it's going to kick out at the bottom. If I try to turn it the other way, it's going to kick in at the top. Right? So it's going to do funny things. And so they have this thing that's really spinning fast. So your angular momentum is I omega, has a big I. Spinning fast has a big omega. Has a really big angular momentum. Person picks up the suitcase, they walk, and then they turn like this, and it goes flying out. They turn like this, one way it comes in and hits them in the legs. And people get all confused. It's a great trick. I have to go on. That one worked so well that they decided, let's take a suitcase and let's fill it up with cement. And then they had people come and try to lift it up. It worked, but it wasn't the best. Then they came up with a real genius model. They put a metal plate in the bottom of an empty suitcase. And they tore out the road and put a very strong electromagnet in the road. And so then they have this little old lady who walks out of the airport and sets her suitcase down on the electromagnet, and she asks the gentleman to help her. And the guy comes, can't lift it up. And then, he's like, I don't know, let's go. She comes over, she lifts it up, no problem. He sets it back down. Very hilarious. I need to point out, it was cool. This big, Dolph Lundgren Scandinavian dude, or Russian dude actually, came and picked up the concrete-filled suitcase and just walked with it like it was nothing. That's what they say. This is not good. There are some people who are just too strong for this trick. The electromagnetic, it still worked. So what we've seen here is phenomena that indicate conservation of angular momentum. Let me go with one more that should be near and dear to many people's hearts. Riding a bicycle. I could ask, how many people here could ride a bicycle? And there might be a person who says no. Most people say yes. Riding a bicycle, of course, has to do with balance. Now let me ask a question that there could be somebody who says yes. How many people can stand on a bicycle stationary without touching the ground, without having a kickstand or anything else, and stay balanced? Anyone do that? There are people who can do that, and I am just so impressed. I do not have that kind of balance. For most of us, we get on that bicycle, and until it's moving, we're unstable. But once it starts moving, we're cool. Why is that? Right, this is physics. We noticed something interesting, that I could ride a bicycle. Shoot, back when I was young and not scared of everything, I'd ride all over the place, no hands on my bicycle. Now I'm afraid, what if something bad happens? That's what happens when you get old. Well, that and you lose your balance a little bit, I probably would fall. Why is it that we can ride bicycles with ease when they're moving, but not when they're stationary? That can't balance when they're stationary.
I guess the faster it's going, the more it resists.
Yeah. You have the angular momentum. As soon as you get those tires rotating, they have an angular momentum, and they're going to resist changing their axis of rotation. And so that helps you to keep your balance. Furthermore, I'm going to put this right next to that so I don't forget where it is. Furthermore, with the tire spinning, so if I'm riding forward, the tire's going to be spinning like that. If I turn to my left, that's going to create a torque, and it makes the tire rotate to the left. So if I lean right, it's going to turn to the right. I said turn instead of lean. If I lean left, it's going to turn to the left. If I lean right, it's going to turn to the right. And so that's why we can easily turn right in no hands, because when you lean to the left, the tire's going to turn for you. Because of conservation of angle, well, not conservation in this case, because of that relationship between the net torque and the change in angular momentum. Okay, before I move on, James, come on up. We'll do the second half of our fun.
With chair first.
Yeah, with Jared. Today is all about James sitting and spinning. I know you guys aren't from my era, but from my era, everybody knew about the sit and spin. Yeah, fun toy for kids to play with. Okay, so now he has no vertical rotation. Now just go ahead and rotate 90 degrees.
Whoa.
So now he starts rotating. Why did he start rotating? You can turn it the other way. Give me some thoughts.
The direction of the torque changes. The net torque.
Okay, we can talk about torque, but it's easiest to only talk about angular momentum. Keep in mind that the net torque in the vertical direction is 0 because he can rotate freely around that axis. The horizontal direction does not have a net torque of 0. That chair has some width. If he leans to the left, the chair will provide a counter torque to keep him from falling over, right? So with that in mind, only the vertical axis should have angular momentum conserved. Because if there's a torque that acts about a different axis, right? If he leans to his left, that's a torque about the horizontal axis that's going this way. So we started, go ahead, hold back. So we started like this. So the angular momentum in the vertical direction was 0. It's pointing this direction. Now if he rotates it, the angular momentum of this is pointing down. His angular momentum is pointing up. So the net between the two should be 0. Now why is it that he's stopping? Friction, right. Because there is some friction in those bearings. So how do we make this the most awesome? We start with it like this with him stationary, and then you turn it 180 degrees. So that's going to give you the fastest change. But all of this is predicated on that one relationship, the bottom one that I had to correct, that relates torque and angular momentum. As always, if you want to play with the toys, you can. Just ask the class. Work. We've been talking about kinetic energy, rotational kinetic energy, 1/2 I omega squared. The rotational equivalence for Newton's second law and for angular momentum, L is equal to I omega is equal to R cross P, and the net torque is equal to I alpha is equal to change in angular momentum over change in time. Work we learned was force dot distance. The rotational equivalent to force, what's the rotational equivalent to force? A force that makes things rotate. What did we call that? The torque. So I replace the force with torque. And then delta x. What do we replace position with in rotational problems?
Theta.
With angle, with theta. And so the work, the rotational work is torque dot delta theta. So once again, it's the same principles. It's just changing from our linear to our rotational variable. Now, with all of this said, when we talk about kinetic energy will now be kinetic energy translational plus kinetic energy rotational. Translational means traveling traveling along some distance. Rotational means rotating around an axis. So if you're riding a bicycle, you have only translational kinetic energy for the bicycle and your body, assuming, of course, you're not going head over heels. The tires have translational kinetic energy because they're also moving with the bicycle, but they're also going to have rotational kinetic energy because they're rotating about an axis. And so when you calculate the kinetic energy for the bicycle, you'd have 1/2 the mass of everything, bicyclist, the bicycle, the tires, times the speed squared, plus, since you have 2 tires, 2 times moment of inertia of the tire, times omega squared, the rotational speed for the tire. And then you would use, since omega is equal to V over R, you can then convert that into also a function of the speed of the bicycle. So if you have a bicycle with 2 equal tires, well, yeah, I'm not going to actually do it here because I don't have space to define my problem. Conservation of energy is something that's going to be on the test. Conservation of energy says that, well, first of all, the first law of thermodynamics, energy cannot be created or destroyed in the universe. That's actually a result of Nether's theorem. Nether was able to show mathematically that energy cannot be created or destroyed. We've been talking only about mechanical energy. Mechanical energy can be transformed into another kind of energy. For instance, in the example of a bullet being shot into a piece of wood, energy was lost from mechanical because it converted it into thermal energy. It wasn't lost completely, it was turned into another kind that we can't easily access. So this is used, this bus is an extreme example where they have a flywheel that they spin that flywheel up, and then they use that as the engine, if you will. So you spin this flywheel, and then you have a transmission, and it's got to be a continuously variable transmission, or you're going to only have certain speeds available. You have quantized speeds. But they use that for the power source, and then you spin it up. It's almost like using a battery, right? If you have a Tesla, a Volt, or a Prius, or something like that, you have a battery. That battery gets charged. You're putting energy in the battery, and then you use the energy from that battery to make the car go. This here has a flywheel. Spin that flywheel to get a lot of energy stored in, a lot of kinetic energy, 1/2 I omega squared, and then you use that energy to make the car move, or the bus. This idea is also used in all of your cars. Although I'm kind of dying, my sister used to own a Boxster, and it drove completely differently than any car I've owned, because I've never owned a sports car. In my car, if I let off of the gas pedal, what happens to the engine's revolutions per minute, the rate at which the engine is rotating? It slows down, but it's kind of slow and slowing down. Right? I let off in the gas, and it's not a quick drop. Whereas in my sister's Boxster, I let off in the gas, and it was like I hit the brake. It was a big change in the engine speed. What's the difference? We call it the flywheel. An automobile uses a flywheel, which is a disc that's rotating with the engine. And the purpose of that flywheel is to make it so the engine has more angular momentum as it's rotating, higher moment of inertia. So when you hit the gas, it doesn't speed up super quick because it's got to also put energy into the flywheel. When you let off the gas, it doesn't slow down super quick because the flywheel is supplying energy back. So it's a way of equalizing things and making it so you don't have as big a changes in the engine speed. Whereas my sister's Boxster, I'm guessing because they wanted to have higher acceleration, they didn't have a big flywheel clearly. I'm sure they had something, but not a big one, so that when you hit the gas, it would speed up really quickly, and when you let off the gas, it would slow down really quickly. It's different driving experience. So there's a practical usage of this that we see. We've already talked about this enough. We have actually 3 students in this class that are in astronomy. And this conservation of angular momentum is important to astronomy. We know that we are orbiting the sun. But the question, why are we orbiting the sun? Why aren't we just falling into the sun? Because the theory is we start out as a big gas cloud, a big nebula. And then something hit it to make things come closer together. If they come closer together, the force of gravity gets larger, because force of gravity is g m1 m2 over radius squared. You decrease the r, 1 over a smaller number is bigger. So the force gets stronger, and then things start being pulled in. But just like with the figure skater, if there's just a small amount of average rotation, when things get closer, they're going to start speeding up to conserve angular momentum. And so we say it spins up. The speed of rotation increases as the material comes in. And collisions makes it become a uniform, flat disk. With us all rotating around the sun, we're not falling into the sun because we have enough momentum that we have the force toward the center, the force of gravity, provides the centripetal acceleration, the acceleration necessary to keep us in a circle. Now remember for the test, centripetal force is never a force you put on your free body diagram. The reason being, centripetal force is mass times acceleration. It's the net force. It's what you get when you add up all the forces on the free body diagram. It's not a force on the free body diagram. So just to, since after all I do want you to be as prepared as possible for the test, let's just take a quick example. When this is spinning around the circle, what forces are acting on the bob? The bob being the black thing.
Centripetal?
No, that's the sum of the forces. What forces are actually acting on it?
Tension.
Okay, gravity down and tension. Ignoring air friction, that's it. Gravity and tension. Gravity's pulling straight down. Tension is pulling parallel to the string. That means it's impossible for this to be in a horizontal swing above my head, first of all. Why is it impossible for it to be horizontal?
Because gravity is pulling it down.
Gravity's down, so you've got to have something pulling it up. And the string, if it was horizontal, would not be pulling up, it would only be pulling in. So it has to have some downward angle. So the vertical component of the tension is countered by the gravitational force, and then the horizontal component of the tension is what's supplying the force toward the center. So when I do sum of the forces toward the center as MA, I'll get force of tension times cosine of the angle below horizontal. And so the force of tension cosine of the angle below horizontal is the centripetal force because it's the total force toward the center. And you don't write centripetal force in your free body diagram, you just put the force of tension on the free body diagram. Had everything to do with tests and nothing to do with today's lecture. Okay, we've already talked about this and about how you can ride a bicycle. So let's talk about some other things and then do a calculation. This here is looking down the barrel of, I believe, a cannon. So what you're seeing here is what's called the rifling. Why do you rifle it? So your shell comes out spinning. Why would you want the shell spinning? It'll stabilize it, keep it going straight. So when people have a rifle means that the barrel has grooves on it to make the bullet spin. Now, of course, most guns have grooves to make the bullet spin. So there's rifling in a handgun as well. But the purpose is to make it stabilize the bullet. So it will be straighter in its shooting. So that's a very practical example of stability. James.
Just curious, if a gun has a longer barrel, that means that it had more time to start spinning, right?
It does. I don't know exactly how they do rifling. I mean, for instance, I'm guessing that the amount of curving in the rifling would change a little bit as you go through because you don't want to start with the same rifle as you end. You're going to have a large amount of friction beginning and less later. But I don't know. That's just my thoughts.
I'm guessing that's why a sniper has a long barrel, but a handgun.
Well, a sniper has a long barrel for multiple reasons. Another reason is the bullet is being projected by a high-pressure gas. And if you have a longer barrel, you'll have the high-pressure gas pushing on the bullet for a longer distance, hence doing more work, making it go faster. So you have that. You have, potential for a faster spin rate, and it's going to have less scatter, even if it wasn't rifled. because you have long distance to make sure it's going straight. Something that no one thinks about is the Earth's precession. And you might say, what in the world is precession, right? Who's heard of the word precession? Not many people. Precession is something that occurs like when you have a top. I totally should have some tops for this, but I don't. If you spin a top, it doesn't just spin vertically, because most of us aren't that good. You always have a little tip, and because you have a little tip, it starts going around like this. You guys know what I'm talking about? That going around like this is called precession. What causes that precession? Well, if it's not perfectly vertical, then you're going to have a torque due to gravity. And so you have an angular momentum that's pointing out here at an angle, and you have a torque that R cross F is pointing, that way. And so then the torque is going to make it so the angular momentum rotates toward the torque constantly and makes it go around, so it goes like this. The Earth does that too. The Earth is tilted 23.5 degrees, 23.4 degrees probably is more accurate. I would say 23.5 instead of most books. About its axis of orbit around the sun. That is, we're tilted to go around the sun. That's the reason we have seasons. When we had September 22, when we had the equinox, that was when the sun was crossing the equator. And now the sun is in the southern hemisphere. Well, it's below the equator. And that's why we're going into the winter season, right? It'll be winter when the sun is as far south as it goes, which will occur December 21, the winter solstice. Okay, so because of that tilt, the Earth's actual, where the North Pole points, slowly precesses. So something like 13,000, 14,000 years is the time it takes for the Earth's precession to go through one cycle. So right now, the Earth's axis points at Polaris. But over time, Polaris will no longer be the North Star. And it will change through different stars because of this precession. Obviously, it's not something you're going to observe in your lifetime because you're not going to live close to 14,000 years on Earth. But when we're in heaven, then we can look back and observe it. Okay, this is our ending. Oh, there's only 2 minutes. Okay, I'm not going to have you calculate. I was going to have people calculate the winter and then do the demonstration. And I will actually do the calculation at the beginning of next class period because there's not time to do it. I'll do the demonstration now and the calculation at the beginning of next class period. So the demonstration is I have a solid sphere, I have a hollow sphere, and I have a solid cylinder. And you can see up there the moments of inertia. The moment of inertia for the tennis ball is 2/3 its mass times radius squared. The moment of inertia for cylinder, 1/2 mass times radius squared. And for this thing, 2/5 mass times radius squared. So I'll line these up basically by size, and we're going to race them. Which do you think will win?
Solid cylinders.
Okay, I have a couple solid cylinders.
Yeah.
It's a solid sphere.
Okay, let's, this ain't. Okay, so let's run it and see. These two, the solid sphere and the cylinder were pretty close, and the tennis ball lagged behind. Now, I think the air resistance has something to do with this. Also, the way I started. In my practice, the solids, or this one won every time, and it shouldn't have. So next class period, I will go through and calculate how we can determine which one would have won. I will add one more thing. If I had something like, let's say, a piece of ice with no friction, so it just slid, how would it have done compared to these? If there's no friction, there's nothing opposing it coming down the ramp. The friction is opposing these things coming down the ramp. The friction is converting gravitational potential energy into rotational kinetic energy. So the actual result here is that the lowest friction would have, if there was no friction, that would have won. because it's not converting any energy to rotation. And the one that has the highest fraction here should be the slowest. So the tennis ball should be the slowest with the highest fraction. The one with the lowest fraction, which would be the solid sphere, should have been the winner because it has the least percentage of its energy in rotation. But I'll do the calculation for that beginning next class period. Remember, the homework that's due today is the one that was originally due Wednesday. I found that I can just delete the problems where you didn't get 100%. So for the 2 people who asked, I deleted the problems where you didn't get 100%. The ones who did get 100%, I just left. Question, Haley? Yes. Yes. Question, Sarah? All right. Have a great weekend. You are going to tackle it. I know you don't want to, but not when you make some fun of that high. Is that what you don't want to get figured out? You're going with not going, you just make
I gotta start doing my homework on Thursday night.
After class? We'll work on that. What we have to do, okay? We cannot have you just sitting around and not starting to work.
I know, I'm literally like,
So we need to be.
it's okay.
Done by 9 in the future.
Yeah.
And just be smart with our time. Maxwell.
For the scrapbook?
Probably not Maxwell, is it?
No, it's just Max.
Okay,
On
for
the
the
scrapbook, do we just add to our other one?
Yeah, it works fine.
And then just turn in the whole thing again?
Yeah.
Okay.
Do you want us to put the entire thing together?
You can have it separate, or you can have
Okay,
it.
because I have it separate.
I mean, in the end, for the final one, I'll want it all together. But for the incremental ones, as long as you have the 5 new ones, that's all I'm going to be grading. Hey, look, it's my astronomy students.
Hey, that's right. I had a problem with my turning in my lab yesterday. I turned it in at like 11:04, but apparently my mover keeps acting up where I have to submit it twice. And then when I got to work at 4 a.m. today, I looked up when I was on the computer, I looked up the lab again, and said that I didn't turn it in. Even though my file says I finished everything at 11:04. Yeah, I turned it in at 4 again, but I swear I did it like 11:04. That's when I turned it the first.
It didn't show that it was late to me.
It didn't show?
No.
Okay, good. Must have been just refreshing my page, I guess.
Because
So
for me, it showed that there were 2 people who didn't turn in, but neither of them were you, and everyone else was on time.
Awesome. Thank you.
For the fourth, for the third test, it falls on a very heavy week for me because I have that Tuesday, I have my Loma Linda interview, and then that following Thursday, I have my PCAT. I retake my PCAT. Is there any possible way to take my physics test earlier or later?
Give me some time to think. You said the third one, so not the one that's next week.
No,
Let me
October 30.
let me think and look at it and get back to you.
Because
Send me an email to remind me.
Okay.
Otherwise, I might not think about it.
Because on that same day that I have my interview, I also have a paper due and a major quiz and then your test. And then that's my morning for those 2 classes. And then I have my lunch break, which I'm probably going to take my interview and then the test. So I don't, I'm trying to plan ahead.
Yeah, which is wise.
Yeah, and I already know that I'm stressing about it that whole entire day.
Yeah, so send me an email and lay out the reasons.
Okay.
So I can think about it and look at the schedule and see what works.
Perfect. Thank you.
Yeah. Mirabal.
I have a question for you regarding grading for core.
Yeah.
I've emailed Dr. McNeil, etc. a couple times because I have no grader, no rubric or anything for the scavenger hunt lab still. Not lab, class period. So in the rubric that's in there now is the one for the selfies for the intro. And so I'm kind of stuck. I have all of the papers still in my folder, and I haven't. I'm like, I can't grade them yet because the rubric is wrong, and I don't know how to set up a rubric in Moodle.
Okay.
And I've talked to her, but she's been so busy with so many things. I've never.
Do you want to go over it right now or at a different time? Because I can show you how to set up a rubric, but do you have the right answers?
Right? No, I don't have the right answers.
Because we need the right answers before we set up the rubric, kind of, you know. But I can show you how to do it. Obviously, you'll need to be checked in and stuff. I don't want to do it without you being checked in.
Yeah.
Or if you record your hours, manually. Okay. So you want to do it?
Sure.
All right.
I'm just tired of having these in my folder.
Yeah. And I'm sure the students are like, what the heck?
I've been trying. But I didn't realize until yesterday that they're doing another panel discussion next week. And I'm like, oh.
Got to get more people lined up.
So I emailed 4 people. I had to try to make it mixed. I'm like, I have all girls in this for the recommendations left. So I had to talk to the office manager, like, I need suggestions. There's not very many
Any boys?
Science department.
Are there any boys who are reasonable?